St. Joseph College for Women, Visakhapatnam. Welcome to St. Joseph's open web-based learning platform, So E-Learn, for its soulful and enriching e-learning experience. Department of Chemistry, St. Joseph's College for Women, Autonomous presents MOOCs, St. Joseph's massive open online course, Metallic and Hydrogen Bond, a modular skill elective course. General Chemistry, Semester 2, Chapter 4, Metallic and Hydrogen Bonds, Module 1, presented by Dr. B. Madhvi, Assistant Professor in Chemistry, Department of Chemistry, St. Joseph's College for Women, Autonomous, Visakhapatnam. Learning outcomes. By the end of this chapter, the student will be able to describe the use of free electron model to explain electrical and thermal conductivity as well as its limitation. The student can able to explain the formation of energy band and distinguish between valence band, conduction band and band gaps. The student can able to identify charge carriers and describe how doping affects conductivity. The student can classify the weak attractive forces between all molecules, including London dispersive forces, dipole-dipole interactions, and dipole-induced dipole interaction. The student can describe the attraction between permanent positive and negative ends of the polar molecules. The student can able to explain how London dispersive forces causes temporary fluctuations in electrons. Contents of this chapter includes introduction of metallic bonds, metallic properties, free electron theory, physical properties of free electron theorem, energy bands, and classification of energy bands. Introduction of metallic bonding. Metallic bonding is a type of bonding found in metallic crystals. A metallic solid can be picturized as a three-dimensional lattice of positive ions with delocalized electrons. Metallic bonding is a type of chemical bonding that holds metal atom together in a solid. In this bonding, the valence electrons of metal atoms are not attached to any one atom but are free to move throughout the entire metal surface. Metals consist of lattice of positive metal ions surrounded by a sea of delocalized electrons. These free electrons move in all the directions and create an electrostatic attractions between the positively charged ions and the negatively charged electrons. This strong attraction is known as metallic bond. Metallic bonding is responsible for many characteristic properties of metals such as high electrical conductivity, thermal conductivity, malleability, ductility, and metallic luster. Factors affecting the strength of metallic bonds. The three main factors that affect the metallic bonds are: first factor is the number of protons or strength of nuclear attraction. As the number of protons in the nucleus increases, the positive charge of metal ions increases. This leads to a strong attraction between the positive ion and the delocalized electron. Therefore, metals with more protons generally have stronger metallic bonds. Second factor is the number of delocalized electrons per atom. Greater the number of delocalized electrons, the smaller is the electrostatic attraction between the positive ions and the electron C. Hence, metals that contribute more electrons forms strong metallic bonds. Third factor, size of atom. The smaller the size, the stronger the force of attraction between the positive ions and the delocalized electrons. Properties of metals. First is the state of metals. Metals are mostly solids at ordinary temperature. However, an important exception is mercury, which exists as a liquid. Second one is metallic luster. Metals have a characteristic shine on their surface known as metallic luster. This shine appearance is due to reflection of light from their surface. Third is hardness. Metals are generally hard substances. However, alkali metals are an exception. They are very soft. For example, sodium can be cut into pieces with the help of knife. Fourth is density. Metals usually have high density or high specific gravity, but alkali and alkaline earth metals are exceptions as they are relatively light. Fifth is heat conductivity. Metals are good conductors of heat, which is why they widely used in cooking utensils. Sixth is electrical conductivity. Metals are also good conductors of electricity. However, their electrical conductivity decreases with an increase in temperature. Seventh one, they are malleable, ductile. Metals can be hammered into thin sheets which are called malleable. They can also be drawn into thin wires which is called as ductile. Eighth property is elasticity. Metals are elastic under moderate conditions, meaning they can regain their original shape after being deformed. They are able to withstand considerable stress. Ninth one, melting and boiling points. Metals generally have high melting and boiling points due to the strong metallic bonds between their atoms. Tenth one, action of light. Metals are opaque, meaning they do not allow light to pass through them. Finally, alloy formation. Metals can easily form alloys, which are solid solutions of two or more metals. These alloys also retain metallic properties and often have improved characteristics. In conclusion, these properties make metals highly versatile and useful in everyday life and industrial applications. Free electron theory or electron sea model. This theory explains the properties of metals by considering that some electrons are free to move throughout the metal. It was developed by Paul Drude and Hendrik Lorentz. According to this theory, metals consist of positively charged ions surrounded by a sea of free electrons. These electrons are not bound to any particular atom and can move freely within the metal. The electrons move randomly similar to like that of gas particles and frequently collide with the positive ions present in the lattice. When an external magnetic field is applied, these electrons gain energy and start moving in a particular direction, which results in electric current. Coming to success of this theory. It successfully explains the electrical conductivity of metals and also explains thermal conductivity of some extent. However, there are some limitations. This theory cannot explain the temperature dependence of conductivity. It also failed to explain the heat capacities of metals and does not account for quantum mechanical behavior. In conclusion, the free electron theory gives a basic understanding of metallic property, but it has limitations. When an electric field is applied across a piece of metal, the delocalized electrons that are already free to move inside the metallic lattice began to respond. In the absence of electric field, these electrons move randomly in different direction because of the thermal energy, so there is no overall movement of charge. Although electrons are constantly moving, the random motion cancels out, producing no current. Once an electric field is introduced, each delocalized electrons experience an electrostatic force because electrons carry a negative charge. This force causes the electron to drift in a direction opposite to the applied electric field, which is towards the positive terminal of the external source. Their motion is not a straight because the electrons frequently collide with the fixed positive metal ion in the lattice and with other electrons. However, despite these collisions, there is still a net movement of electrons in one direction. This net movement is called as drift velocity. Millions of electrons drift together through the metal charge is transferred from one end to the conductor of the other, producing an electric current. The positive metal ion remains locked in the regular lattice position and do not move from place to place. Only the mobile delocalized electrons are responsible to conduct. The ability of these electrons to move freely through the structure explains why metals are excellent conductors of electricity. A stronger electric field exerts a greater force on the electron, increasing the drift speed and therefore increases the current flowing through the metal. Explanation of physical properties of metals on basis of electron C model. Metallic cluster. The shining of metal is due to presence of delocalized mobile electron. When light falls on a metal, the loosely held mobile electrons absorbs protons and start oscillating. The absorbed energy is immediately re-emitted in the form of visible light. The momentary exchange of the light energy possesses the metallic cluster characteristic of the metal. Second property, electrical conductivity. The electrical conductivity possessed by a metal is due to the flow of mobile electron. When the potential difference is applied across a piece of metal, the electrons began to move towards the positive terminal. These electrons are simultaneously replaced by the electrons coming from the negative electrode into the piece of metal. Thermal conductivity. When a metal is heated in certain part, the kinetic energy of the mobile electron increases. The energetic electrons moving in this part move rapidly to the cooler parts and transfer their kinetic energy by means of collisions with other electrons, which in turn get energy and move farther. Thus, heat gets conducted from one part of the metal to other. High tensile strength. Metals possess high tensile strength. That means they can be stretched without breaking. It is due to the presence of strong electrostatic attraction between the positively charged kernels and the mobile electrons present around them. Limitations of free electron theory. This theory is unable to explain why does the electrical conductivity of some metals decreases linearly with increase in temperature while that of others does not. This theory also unable to explain why certain metals behaves like semiconductors in the solid state. Energy bands. In gaseous substance, the arrangement of molecules is spread apart and are not so close to each other. In liquids, the molecules are closer to each other, but in solids, the molecules are closely arranged together. Due to this, atoms of molecules tends to move into the orbital of neighboring atoms. Hence, the electron orbital overlap when atoms come together. In solids, several bands of energy levels are formed due to their intermixing of atoms in solids. We call these sets of energy levels as energy bands. In an isolated atom, the electron in each orbit possesses definite energy. But in this case of solid, the energy levels of the outermost orbit electron is affected by the neighboring atoms. When two isolated charges are brought close to each other, the electrons in the outermost orbit experience an attractive force from the nearest or neighboring atom nucleus. Due to this reason, the energies of the electrons will not be able to same. The energy levels of electrons are changed to a value which is highly or lower than that of the original energy level of the electron. The electron in the same orbit exhibit different energy levels. The grouping of these different energy levels is known as energy band. However, the energy of the inner orbit electron is not much affected by the presence of neighboring atoms. Classification of energy bands. Valence band. The electrons in the outermost shell are known as valence electrons. These valence electrons contains a series of energy levels and form an energy band known as valence band. The valence band has highest occupied energy. Conduction band. The valence electrons are not tightly held to the nucleus, due to which a few of these valence electrons leave the outermost orbit, even at room temperature, and become free electrons. The free electrons conduct current in conductors and are therefore known as conduction electrons. The conduction band is one that contains conduction electrons and has the lowest occupied energy levels. Forbidden energy gap. The gap between the valence band and the conduction band is referred to as the forbidden gap. As the name suggests, the forbidden gap does not have any energy and no electron stays in this band. If the forbidden energy gap is greater, then the valence band electrons are tightly bound or firmly attached to the nucleus. We require some amount of external energy that is equal to the forbidden energy gap. Thank you.